Well, hello and good afternoon. Welcome to this high temperature heat pumps update webinar. And today we're going to be exploring the world of high temperature heat pumps, which are no longer constrained to just under 100 degrees. If you think back just a couple of years ago, we were very excited about a heat pump that might be able to do 120 degrees. And then if you go back just 12 months, we were very excited about a heat pump that might be able to do steam or 160 degrees. What temperature are we up to today? Where are we at with R&D? Well, stay tuned. We're about to find out. So good afternoon. My name is Jared Leake and I'm the CEO for the Australian Alliance for Energy Productivity. I'd like to welcome you to this webinar. And may I start with an acknowledgement to the traditional custodians of country throughout Australia and their connections to land, sea and community, and pay my respects to elders past, present and into the future as well. For those of you that are new to A2EP, we are a member-funded non-for-profit organisation driven to improve the energy productivity and to decarbonise manufacturing, transport, commercial and ag sectors within Australia. And here is our beautiful cross-section of members. And without their support, we would not be able to bring you things like this webinar today. So a big shout out and a thank you for that wonderful members that we do have. Just a touch of housekeeping. The slides will be distributed to those that are registered next week, along with a recording. We are really hoping to take questions today. We've got a lot of material to get through, but we're hoping we'll get through to the questions. So if you do have something, put that in that Q&A box and upvote someone else's question if you like, or feel free to have a little side panel chat in the chat box there. Joining me today, I have Professor Gary Rosengarten. Gary, thanks for joining me today to co-host. And for those that you don't know, Gary, he is the professor there for RMIT University, and probably along with UniSA, the main organisation, research organisation in Australia, looking at heat pumps and all things renewable heating. Gary's done plenty of years working with things like solar thermal, and is one hell of an authority on this subject. Gary, welcome, and thank you very much for joining me and helping me host today.
Thanks, Jared. Looking forward to it.
Our speaker today that we have is dialing in from Switzerland, an early morning there, is Dr. Cordin Arpagaus. And this is Cordin's third year in a row, I believe, doing this presentation for us. And it is one of our most watched webinars that A2EP does. Cordin is a senior research engineer from Eastern Switzerland University of Applied Science and is really a leading global researcher when it comes to heat pumps. Anytime that you're reading something on industrial heat pumps from the IEA or the European Heat Pump Association, fairly well guaranteed if you're looking at the references there, Cordin is the one that's referenced. His work is really guiding a lot of research and public policy and what have you within heat pumps. Now, if I go back just 3 short years, as said before, we were getting very excited about heat pumps that might get to 120 degrees or so. And then last year we had a presentation, we're showing a lot with steam heat pumps and things happening there. Cordin, I know there's been a lot of R&D over the last 12 months. I'll get you to share your screen and please take us through what's happening.
Thank you very much, Jared, and also hello, Gary, to having me again in this webinar. I'm very happy to present some overview and update on high temperature heat pumps and for the Australian Alliance for Energy Productivity. So this is also work with my colleagues at the Institute of Energy Systems at the Eastern Switzerland University of Applied Science. I hope that I can skip, yeah. So today I have some engineers that will help me through my presentation because it's a very, let's say, man-dominated field. I have here some women engineers And so I will start with a short motivation, then go to the state of the art of high temperature heat pumps. I will explain some realized examples. We speak about refrigerants, which are sustainable. Then I have some slides on business models and some economic conditions. And finally, I'll summarize and conclude my talk. First, just some advertisement, let's say, from our side. We have published quite some talks so far, especially on high temperature heat pumps. And here you will see some QR codes that lead to the videos that we are have on our YouTube channel from our university. So steam generating heat pumps is really a topic that comes up very often now, and it's hitting the nerves of the time, I think we can say that in English. On 18th of March, we have another webinar organized from our university, and is very worthwhile to maybe also follow if you have the time. Then there is another webinar organized from the European Heat Pump Association on 3 projects. Spirit, Push to Heat, and SUS Heat. They are all funded by European money. So this is also very worthwhile to attend on 14th of March. So what is the motivation to heat pumps, and especially heat pumps at higher temperature for industrial applications? It's upgrading heat from a lower temperature to a higher temperature by using electricity. So today, an industrial company is typically using a chiller, which is electrical driven to produce cold for cooling processes. But they are producing waste heat, which goes to the environment typically, and that is a useful heat for a high temperature heat pump to upgrade it again to higher temperatures. And then looking outside of the company, we have some other possible heat sources that could be used in heat pumps. First of all, the environment with ambient air or geothermal heat, lake water, river water, or solar heat, but also then industrial companies that have waste heat that would be available, or some power plants or waste incinerator plants, which would feed a district heating network as a possible source. So there is a large heat energy demand, and this is the energy demand for the European industry. Around 66% is process heating, and from that around 37% of it is below 200 degrees. So this piece of the cake is a potential for high temperature heat pump for heat upgrade technology. For the higher temperature requirement, over 200 degrees, will be some other hopefully renewable technologies that could fill the gap, because today this is mainly produced by burning fossil fuel, and that's the motivation to decarbonize process heating and the energy demand in industry. So heat pumps are a key technology. This has been recognized, especially for this, let's say, still lower temperature band. There we have different sectors that we should address with this high temperature heat pump technology. Here again, some data that is structured by temperature level. And you also can see here between, let's say, process heat 80 to 200 degrees, we have a sum of around 30%. We look at it at the industrial sectors, and you see the paper, pulp, and print sector has potential for 150 to 200 degrees. Then mainly food and tobacco, food and beverage, in this below 150 degree. And then we have the chemical sector as well. But here some numbers of terawatt hours per year for first, let's say, potential calculations. Then we have the different processes in the different sectors, and here visualized by colors and temperature levels, where these processes typically operate. And we can overlay somehow the heat pump technology. So if a heat pump can generate, let's say, 80 degrees supply temperature, then these light blue processes could be covered. If we have heat pumps that can go to 100 degree, also the darker blue parts can be covered. And when we go to very high and high temperature heat pumps of 140 or higher temperature, we can also cover then processes like, for example, distillation or drying or evaporation, pasteurization in food sector. So this will offer more applications to cover with heat pumps. Always we need a heat source, that is a requirement, but yeah, it's always some thinking steps where to then integrate the heat pump, but it shows a little bit the applications and where to. Then there are also some studies that come up with a number of heat pumps as a potential. Here the study on an estimate for the European market. Here 4 sectors: the food, paper, chemical, and refinery sector. Here with cumulative process heat and waste heat numbers. And on the top we have the process heat curves, and below the waste heat curves. And the idea would be to make use of that waste heat at temperatures between 20, 40, 60, 80 degrees maybe, and upgrade it to higher temperature, to process heat higher than 80, 100, 120, up to 200 degrees. So then assuming that all that potential could be covered, and assuming a heat pump size of 3 megawatt, this would generate 4,174 heat pump units. So it's an estimate, but for sure there are many heat pumps, potential applications for heat pumps, for sure in this 1,000 to maybe also 10,000 number region. So, but today there is a lack, so this is still potential, and so that is why we also make presentations to make aware, to increase the awareness of this high temperature heat pump technology. One of
Gordon,
the important.
I just
Sure,
grab you
yeah.
there for that last slide. That's intriguing. That is, I've got data envy there. I really wish we had that for Australia. That's fantastic. And maybe we'll reach out to Marina et al. And the team there to see how they went about this piece of work. Any ideas of sort of how long this took to put together? Or did you work on putting this data together as well, or just know the people that did that?
Yes, I know the people in the Netherlands, Andrew Marina and his team. I was a reviewer of that paper actually as well, and I especially like this visualization of this potential with these graphs. And so they have a big database where they had the opportunity to publish. So because such data is not always, let's say, freely available. So for sure, so if you would click on that link of that paper, there will be an additional appendix, I think, to where the different processes are listed. So that is worthwhile to follow this link to this journal for renewable and sustainable energy reviews.
Brilliant. And Gary, I think we've got our first research piece and homework to do, mate.
We've kind of got, we started this on the Race to 30 opportunity assessment. That's the top, the demand. We don't have the data for the waste heat that I've seen anywhere in Australia, but I can't imagine the waste heat being that different in Europe in those sectors compared to Australia, but it may be.
Yeah, I tend to agree. The amount of waste heat and the temperature profile for their paper sector is going to be very similar to ours. So we can probably steal a little bit from that and start utilizing that. So good stuff. Thanks, Cordin. Back to you.
Okay, yeah. So it's for sure worthwhile to study the waste heat potentials. And by the way, I would call it more like excess heat instead of waste heat. So it's a more positive term. So excess heat means it's still useful for some processes, and especially as a heat source for the heat pumps. If you would do some literature research, I would also use the keyword excess heat. So this, I'll continue here with the second part. Now it's more about the heat pump technologies. And here we have this Annex 58 projects from the IEA, where 14 countries were participating, and we are really at finalizing these project results. Is the lead from the Danish Technological Institute from Benjamin Zülsdorf as an operating agent, and this annex is quite successful. So many contributions were there, and they are now summarized in some reports. And the task 1 report is about the different technologies for high temperature heat pumps. It's really worthwhile to visit, and also it's possible to download a large report, and gives this overview of the suppliers, demonstration case studies, and national perspectives of 13 countries, and so on. And I will also use some of the results from this report. What I'm especially interested is the fact sheets on the technologies, which includes performance data, capacity ranges, temperature range, working fluid, the refrigerant that is used, compressor technology, investment cost, TRL level, technology readiness level, lifetime, size, and some examples. So this slide is trying to summarize a lot of this report, and it also includes some additional companies and manufacturers of high temperature heat pumps which are not in the report actually. So it's really a, let's say, state of the art overview. On the left we have a diagram showing the heat supply temperature that this heat pump can achieve. A maximum. It starts at 100 degrees Celsius, goes to 280 degrees. And then we have the heating capacity in megawatt terms in a logarithmic scale. So we have here 1 megawatt, 10 megawatt, and here 100 kilowatt. And it is structured by temperature band levels, and also colored in yellow, blue, and red for the different compressor types. So in this Annex 58, we also included the vapor recompression technology as an open heat pump cycle. So it means steam, the vapor recompression to higher pressure. So this means also higher temperatures and higher pressures are achievable. Not only looking at closed cycle heat pumps, where the cycle is, let's say, limited by the thermodynamic properties of the refrigerants, by the critical temperature. So what can we say? There is a wide range of capacity available. Also temperatures higher than 200 degrees are actually possible. And we see that the turbo compressors are more in the high capacity range. The pistons or reciprocating compressors more in the lower capacity range, and maybe the screw compressor somehow in between, but it's really depending on the compressor manufacturer. So you see here different company names and also different brands, and the diagram can be used somehow as a selection diagram to come up with some potential products. When you look at the company's headquarters, we see that they are here mainly in Europe, especially in Germany, and also in Norway, in the Scandinavian countries. But some companies have worldwide distribution. Some others are more local based. So it really depends about how to get the heat pumps into the market, and to have suppliers that will deliver the heat pump to the particular country and site. Then there are some other companies in Japan, for example, and for sure there are others which are not listed here in this on this table, but these companies here were participating and helping also in the IEA project. An important parameter is the technology readiness level as a measure how far the technology has developed towards market. And so usually we have 9 readiness levels from 1 to 9. And the first ones from 1 to 4 are more in the lab scale. So trying to validate the technology in the laboratory scale. This is typically university work as well. And the university research projects are involved. Then there is prototyping. The scale up of the technology starts, and the technology is demonstrated in a relevant technology environment in the industrial side, and it is demonstrated. Then if the technology passes this stage, it goes to system prototype development, so in the operating environment, and then it's really showing that this technology proves in operating environment, which means the technology is gaining operating hours, and then after the technology is really market ready. And from the technology point of view and from the temperature point of view of heat pumps, we came up with some temperature levels. So we would say 80 to 90 degrees is really established, and there are many products available. 100 to 150. There are some already in the market, but some are still in the system demonstration stage. And then for sure there are several research institutes and universities which have labs and labs units to prove the concept, and also to validate the technology in the lab up to 200 degrees, maybe also higher temperature. So this list of the IEA companies there is here listed in a table. You have here the company names, again, the product name, the capacity, the temperature, and the technology readiness level. So we see now 9 is the highest level, and there are several which reached that stage. And there are other suppliers also listed here in this smaller bullets list, and other companies. So the time or the development goes towards the to the right, so pushing these technologies to market. So we have in this list 23 market-ready technologies, 7 prototypes and demonstration systems, and 3 lab-scale prototypes. And yeah, that's a first overview. On that slide, we see some operating maps of industrial high-temperature heat pumps, and this is a map that is typically used for the end user. So the end user knows, okay, I have a waste heat temperature of, for example, 40 to 60 degrees, and I would like to upgrade this waste heat to 100 degrees, 120 degrees as a supply temperature. So they would end here at this point here, and we have overlay of several operating maps, and we see here a concentration of maps. So this means there are several products available that can fulfill this requirement, and some reach even higher temperatures, some others covering a wider field, a wider map. And yeah, it's always important to get these operating maps from the different heat pumps. Now I have some slides of particular systems. So here, the first is from the company Enerin. Enerin is a Norwegian company, a smaller company, and they have the so-called temp heat pump, which is a high-temperature heat pump. It's based on a Stirling cycle with helium as refrigerant. So helium is R704, so it's a anorganic or a noble gas, and the number, so it's a 7 from the refrigerant nomenclature, and 4 is the molecular weight of helium, so 704. It's inert, 0 global warming potential, no ozone depletion potential. So from the environmental point of view, very attractive. This has a 400 kilowatt capacity, and with this system, it is also producing steam. Here we can see a steam generator from the company Vaterus from Finland, which is then connected to the heat pump. Here we see an example of a pilot that is running in IVAR company. They are doing works with biogas, and they need steam for CO2 removal from biogas. So this heat pump produces here 2-bar gauge steam, which is 134 degrees. It has been installed in June 2023, and it's now operating. On that graph, or in that figure, you see the system in an isolated situation. So it's important to reduce the radiation, or to lose the heat. The system needs to be very good isolated, especially at higher temperature. So this has been published here in different papers and conference papers. So you can click on that to get the paper. On the right, you have some COP data of that system. And the advantage of this Stirling heat pump, cycle heat pump, is that it achieves very high temperature lifts from source to sink. So from 21 degrees, let's say, source, to 139 or 199, still a COP between 1.5 to 1.8. So 1.8 times more efficient than an electrical heater. We cannot change the thermodynamics, but we can try to, let's say, improve the technology to get closer to the Carnot efficiency or to the highest theoretically maximum efficiency. So they continue with their company and with their products. So their next goals and steps is to commercialize more and more installations, and also to increase the supply temperature to 250 degrees as well. So this in a European funded project. That's their development perspective. Then we have the company SPH that I would like to mention here, because they achieve very high temperatures as well, and especially steam generating heat pumps in a size that is very attractive for many companies. So I expect they get many requests for their heat pumps. Here you see the system. It's installed quite modular way. So they have some heat exchangers, the compressor. Here again, the steam generating heat exchanger from Vaterus. And so they can design the heat pump cycle depending on the requirements. They have a piston compressor, 4-cylinder, and multiple of them are possible to increase the capacity. They have the option to use synthetic refrigerants, these HFO refrigerants, which have low global warming potential, but also they offer systems with hydrocarbons like butane or pentane. So this is a picture of their lab where they test the systems. So this is as a heat pump manufacturer. It's needed. It's a test stand is needed for the heat source and heat sink to simulate, let's say, the environmental conditions. And because this is industrial scale, it needs a quite large lab to also reach, let's say, 1 megawatt of heat supply, and then recycling that heat again is maybe the most important thing for such a test lab, to reuse the heat generated by the heat pumps during the tests. So here are two examples of realized examples from this so-called therm booster. One is in a gelatin production, and they produce here steam at 2 bars with for 514 kilowatt heating capacity. The heat source is here waste heat at higher temperatures, let's say 85 degree. So they achieve a COP of 4.4. And here another one, thermoplastic from waste as an application. Here the application is a drying process. The system is like double the size, or like 2 cycles on one such a rig. So they achieve 809 kilowatt nominal power, cooling power, 1017 heating capacity. And this is a system they have for our Push to Heat project, which is a European funded project where our university Ost is also participating as a Swiss university. We are still allowed, let's say, to participate in European projects, and that's the system, the heat pump that will go into a paper factory from Felix Schöller Group. So it's a 2-cascade system with piston and screw compressors. Here you can see the piston compressor, the motors, 2 compressors here, and here the screw compressors, the heat exchangers, and again here the steam generating heat exchanger. The refrigerant that is used is in the first stage R515B, and then the second stage the R1233ZD. This is all on a rig, and then finally placed in a container solution which you can see here on the bottom. The application is a drying it's a paper factory using the exhaust air from the dryer as a source, as a heat source to generate a low pressure steam. So you see here the temperature lift. The air, the humid exhaust air is there is first a heat exchanger that produces then a water glycol circuit, which goes then into the heat pump as a source, and it generates steam. The COP 2.3 capacity 1180 kilowatt, which is 1800 kilogram of steam per hour. So another very interesting application. And I want to mention especially this steam generator and condenser from the company Vaterus. We have seen it now several times in these systems. So the company has really the knowledge and competence to produce these heat exchangers. These are so-called plate and shell heat exchangers, and they have an additional water tank here on the left to stabilize the steam production. So here we have it in a color visualization. We have here the water that is fed into this heat exchanger from the bottom. Then we have the refrigerant, which would be, for example, the R1233ZD, this HCFO, which is the hot part. It gives the heat to the water evaporates, the water in the tank or in this shell, shell of heat exchanger is evaporated, and the steam is generated here on, which leaves the heat exchanger on top. So this is really direct heat exchange. So this is, let's say, the most efficient way. There is no other media in between. So that's the smallest pinch temperature in this heat exchanger, so it makes it most efficient. The shell is used as a steam boiler, and it is fully welded and very robust. These plates are in a circular shape, so also welded in a very compact and lightweight design. And also this heat exchangers can be, let's say, cleaned very easily. There are no gaskets, and so it's very robust system, so used especially also in these steam generating heat pumps. Then I have here a slide which came into my mind as well from Atmos, a company in the US, which want to commercialize an air source steam heat pump. So first was thinking this is quite a challenge, because the temperature lift will be very high from ambient air to steam. But after reading and discussing with this company and the people, I also understood that could be quite a potential system for many applications, because this system is not using, let's say, waste heat from industrial company, or doesn't need, let's say, a ground source or geothermal. It's simply using the air of the environment which is there. And so the COP will not be so high, but still high enough to be economic compared to an electrical heater. So it's still 1.8 times more efficient. More detail than that here shown on the slide, I could not organize in the lack of time, let's say. But what I know is they have this heat pump with a two-stage cascade cycle. So with a first stage using glycol, which goes to the heat exchangers, the air source heat exchangers, and then a second stage with another refrigerant, with an intermediate heat exchanger, then to produce steam. So the idea is to place the air source heat exchanger somewhere on the roof, maybe also on the container directly. So it's a system that could be integrated in a city. So like chillers today. Then, okay, using the electricity, which is renewable. So overall, a system that is zero carbon emission. That is the final goal. And they have also first pilot projects with the company New Belgium Brewing. So to then demonstrate this technology. So we will expect hopefully good results in the next years with this system. Then a realized example of a high temperature heat pump, which has been cited now several times, especially in LinkedIn posts and so on. It's in Ireland, the first zero emission distillery. It's called Ashgarash. I'm not sure if I spell it correctly. It's Irish. But they have a heat pump that can generate up to 120 degrees. They actually need it for 115 degrees for the distillery process. 1 megawatt heating capacity. It's used for heating and cooling, so it makes the heat pump principle. It uses really the both sides of the heat pump. Here you see these are actually 3 heat pumps from the company Oilon. 2 times this P450 series heat pump that can go to 120 degree, and 1 150 series heat pump for a little bit lower temperatures. And they managed to split the heat demands into several temperature levels, and this increases the system efficiency. So that's another important point. Not only reaching, let's say, always the highest temperature needed, but really doing the energy analysis of the processes and then decide where to integrate and the heat pump. Then another application and example is for drying. This is Geland Counterflow. This company is producing electrical dryers in larger scale, in this case for pet food, and they electrified this drying process, and they use heat pumps. They have these heat pumps from the company Kombitherm from Germany, and here you can see how this system is realized. So this is a system in Norway that is drying, let's say, fish food, aqua feed. And there is a nice video that you would click here that illustrates this heat pump and dryer technology. They are using here 4 high temperature heat pumps with, from Kombitherm, 3.5 megawatt heating capacity. There are R123ZD as a refrigerant. Screw compressors from the company Bitzer, which allow this high temperature compression, and then using intermediate circuits for then bring this heat then into the dryer. So a very nice application, and as far as I know, they have now several requests for this electrical dryer around the world, so they can multiply this system and have a good economic perspective, I think, with this technology.
Brilliant. That's looking good there, Cordin. That's a lot of different options there, and I'll be sure that Mars and Nestle find out about this Geland Counterflow. Now we're running a little bit short of time, and Gary's typing in some questions there for some people that have come through. Gary, any question for Cordin there?
Not right. Well, there's a few, but I think there's quite a few in the chat. Is it worthwhile going through, giving people in the chat? There's one around the refrigerants, but we're getting onto that later, right?
Yes, we are. So
Yeah.
we'll hold that one.
Yeah. That one. Yeah, no, I think I'm happy to move on so we get a chance for the audience questions.
All right. Thanks, Gary. Yeah, and you and I will type in questions that we know the answers to. Otherwise, let's keep moving. Back to you then, Cordin.
Okay, great. So I go to the into the topic of refrigerants. I try to speed up. So from the annex technologies that we have seen before, I made this graph. We can see that mostly natural, let's say natural refrigerants are already implemented in the high temperature heat pumps. So this means systems with steam, so water as a refrigerant, R718. So then CO2 as well, ammonia, and then hydrocarbon systems with pentane, butane, propane. And then we have seen as well helium and other noble gases, which I would also count to this natural type of group of refrigerants. Then the second group is the HFOs, hydrofluorolefins, with these synthetic refrigerants, the red ones, and then some still using HFCs in these systems, but they will be replaced by synthetic HFO refrigerants in the future. So this is a short overview. The trend is really towards hydrocarbons, and I did a questionnaire or a review of some heat pump manufacturers, actually 14, and I asked them about their refrigerant. So which refrigerant do they actually or currently use, and which they are planning to use in the future? And the main selection criteria for the refrigerants are here: the thermodynamic suitability, so that the refrigerant works in this temperature range that is needed for evaporation and condensation in the heat pump cycle. Then we have the environmental aspects, so that is a refrigerant with no or very low global warming potential, that it has no ozone depletion potential because it's forbidden, then that it does not produce some other acids also when they get released accidentally into the environment. And then efficiency in terms of COP, the advantage of heat pump technology. And so what we see is that okay, they use HFOs, hydrocarbons, and hydrofluorocarbons less and less, but hydrocarbons, yes. So we see a trend towards that. Ammonia is still there, carbon dioxide, CO2, and water. And what would be the developing time to shift from a synthetic refrigerant to a natural one? And then that was a second question in the survey, and the answers were between 6 months to 5 years. So it's a time frame which is I would expect typical to develop to a new heat pump technology. Up to 5 years would be necessary. So that's it's also a statement that these refrigerants are very much discussed, and there is a trend towards natural ones, but also the synthetic ones. Especially in Europe, we are looking at natural refrigerants, but in other types of the world, other regions of the world, some synthetic refrigerants will also be accepted. So it's mainly the regulation and the environmental view that determine or that push the refrigerant selection. Here we have a graph showing different temperature ranges for the different refrigerants. Here we have again the HFOs and the natural ones. Here you can see how these are built chemically. So the HFO 1336 MZZZ, the Z isomer has here a double bond in the carbon, which makes it very, let's say, unrobust. When it would go into the environment, it will degrade quickly, will not stay long in the atmosphere. Then we have fluor atoms and hydrogen. So these are the typical building blocks for these HFOs. Some also have a chlorine atom, here the 1,2,3,CZD, and that could be a problem because the ODP, the ozone depletion potential, is not zero. It's 0.0034, so almost zero. But yeah, in some countries this is prohibited. So, but some have exceptions. So the selection, yeah.
Just right, because we're running just a touch behind schedule, should we jump over a little bit or just speed up a bit on this refrigeration one? Can we do that?
Yes. So, okay, one topic is TFA, the trifluoric acetic acid, that would be produced when some refrigerants go into the atmosphere. And this is really depending on the chemical, on the degradation pathways. We can say if the chemical has CF3CF double bond group, then it goes 100% to TFA, and others not. So it's really, the message here is not every refrigerant has the same yield in TFA. Yeah, that's it. Yeah, that's the last slide on the refrigerant. Then I would go into more market view. If okay, I continue here. So this is the market diffusion of technologies. And normally we have the innovators that start with the new technologies, then early adopters, early majority, late majority, and laggards. And for the heat pumps in domestic scale, so for the house, single family houses, buildings, this is already at 65% in Switzerland, for example. So this is already going over the majority. So there is no need for, let's say, subsidies, or yeah, it's nice to have, but not necessarily. But for other technologies, to push it, some subsidy would be needed, and this is happening for the industrial heat pumps. Here we are really at the beginning, at 1% probably. There are not so good data, but I would expect it here. And so there are some business models for heat pumps in industrial scale, and we can summarize these along the value chain. So first, a heat pump manufacturer needs to have R&D, then manufacturing, maybe then consulting, planning, sales, then installation of the system, maintenance, and running and controlling, and so on, different activities. And now one company could only, let's say, sell the technology or licensing the technologies. Others may sell the product really to a business focus, to a reseller or installation partner. Then there is this business model of direct to customer, so directly sell the heat pump to the customer and also give them a service contract for the maintenance work. Or there are some other models like leasing, and then at the end, heat as a service or energy as a service with energy contracting. So when you're going towards the right part of this value chain and including a lot of it, then we got closer to the customer integration. So we also call it solution or servitization. And then we did an overview, a review survey with 16 manufacturers. Yes, Gary?
Can we go straight to the next slide? The market.
Yeah, I was thinking we'll skip this one. We'll skip this one. Yeah,
I skip it. Yeah. So the message is that here we have purchase or direct to customer is really the most often used business model. There are some barriers to implement or to to make this market diffusion or adoption better. And these are here some other review. So there are some barriers in knowledge and information transformation, then some in the costs sectors, let's say, and then technology and processes. The first and most significant barrier is costs of fuel and electricity. So really the energy prices. Then we have this the investment is also maybe too high in some cases compared to alternative technologies like an electrical heater or a biomass or biogas. Product acceptance, so it's another important factor. So knowledge exchange, the people need to know that this technology is available and how to integrate this. These are barriers here for knowledge, information. Some good engineers are needed that are knowledge to integrate systems, energy systems in a process. Yeah, there are several barriers here, and I would expect they are quite similar in all other countries as well. Then we have this market attractiveness, which is based on the electricity and gas price, on this price ratio. And here we have the map from Europe, and in color the price ratio. So if the electricity price is low, then electrical driven technologies are more in favor, and this we can see here mainly here in the Scandinavian countries. And the darker the lower the gas price, and then some fossil fuel systems are more in favor. Now this is a graph with the price ratio by the end of October 2023 from Eurostat for a small scale industrial end user. And so the ratios changed a little bit, but yeah, overall still quite yellowish, let's say, which is not, it's good for the electrical systems. But anyway, this ratio has to be evaluated really on the end user level, very locally, with the different energy contracts the company has on site. Typically, electrical contracts are more over, let's say, over a year, long term, and the gas is bought on the spot market, more quick, more short time. This is the COP. I think I've shown this several times. Okay, the efficiency is really depending on the temperature lift, so we can skip.
Yep.
And this I also showed in other presentations. So it's just showing the link between the price ratio and the COP. So this means if you look at the red curve, if the price ratio gets smaller, so electricity gets cheaper, then an economic temperature lift for the heat pump gets also larger. So this means, yeah, so with a ratio of 2.5, 80 Kelvin lift is still economic compared to a gas boiler from operating point of view. So the costs are like in parity, in parity situation. So this means if we have 40 degrees waste heat and 80 Kelvin lift, 120 degree supply, so low pressure steam with 40 degrees waste heat would be economic. If the price ratio goes further down, even 100 Kelvin gets economic. So it's a illustration how this is related together.
And
Um,
we might leave it there, Cordin, just so we
mhm.
finish close to on time. That's a
Okay.
fantastic summary there. And that's really, really helpful. Gary and I have been talking about this electricity to gas price ratio in Australia. It's very hard to come up with a number that's similar there because of our very much fluctuating prices once you start having a lot of renewables in the grid there. But we probably won't dive into that one. Gary, you've been monitoring the questions there. Anything that we could give to Cordin now in the last few minutes?
There's a bit on the refrigerants, but I think there's some specific stuff from John Fetz, and if you want to answer that, but that's very specific on global warming potential. There was a general one by Kyle. What design parameters in heat pump technology presents the largest barrier for reaching high temperatures for high pressure industrial steam? So what are those key design parameters that are sort of holding us back, or which will allow us to get this technology rolled out, other than the economic value?
So the heat pump is manufactured it's a system made of different components. One component, the most important one, is the compressor. So then we have the valves, then we have heat exchangers. So all these components have to stand high temperatures and high pressures depending on the refrigerant. So these components have to be developed so that a heat pump manufacturer can then design the heat pump system. And so this is the major barrier. So the whole components product families need to be developed to higher temperature level. And now we see that the compressors some are ready for higher temperatures, and now more heat pump products will be available.
Yeah, and it's good to see the likes of Vartaros and Alfa Laval coming up with these new components to handle those high pressures. That's what we need. And I'll take a question here, throw one in there. Is from Tim saying, is it better to generate low temp steam at vacuum with a falling film evaporator, or use an intermediary refrigeration cycle with a plate heat exchanger, say? One is compressing steam directly, like an MVR. In the other case, you do it indirectly via the refrigerant. What's your opinion on that one? Which is there a clear sort of way to go in that case?
Yes, that's a good question. Here in this presentation, I didn't show this vapor recompression with the Vapo vents and so on. Here I showed the direct steam generation, the heat exchanger. The advantage is that with the direct steam generation, we have fewer heat exchanger steps. So we can save some delta T, which is efficiency. So that is the major advantage. But the other system with the vacuum recompression is also very efficient. We analyzed this also theoretically in some papers where we have some comparison. The challenge there is to have this steam recompression, the suction pressure that is below 1 atmosphere. So the system has to be vacuum tight, and that is not every company can manage that. But there are some companies, and they are very successful with this vacuum recompression.
Good. And we know some big industrials that are heading that track, looking at 7 or 8 of that pillar MVR in series. With just the final minutes or so, Gary, anything else to throw to Cordin or from the audience?
I just wouldn't mind asking this question, and it's what you were saying, Jared, before about our huge variations in our electricity spot price because of our large penetration of renewables, in fact, the largest in the world. So you can make these systems with demand management much more profitable, anyone installs them, by having storage and then turning them on when spot prices might even be negative, when you can make a profit. But can the different compressor technologies respond reasonably quickly, or do they need a time to warm up and cool down? You can't be turning them on and off reasonably rapidly. I guess that depends whether it's a piston, etc.
So the response time of the heat pumps is shorter than than maybe thought. It's in the order of 5 to 10 minutes. It's not hours. So the compressors are ready to operate in part load, and this part load operation. And so if the system is warm and not cold, like in the morning or so, it can shift to other operating points in quite short time. So I would expect this in, let's say, 10 minutes, 5 minutes, 15 minutes. So, but the storage is very important. So I didn't cover that, but I think the storage on heat source and heat sink are very, very important. And there are many applications which are not continuous, so more batch processes. And then the storage tank in principle also determines the size of the heat pump.
Absolutely. Well, that's good to know then, Gary. I mean, 10 to 15 minutes, I guess that should be enough. And if certainly the quicker the better to be able to react to renewables. So this is quite promising, I guess. Happy with that one, Gary?
Yep. You can't play in the FCAS market really, but other
No.
Yep. Thanks.
At least do a little bit of arbitrage. Good. Okay, look, and we're well over time, and sorry for going so long here today, but there's such great content coming through. Thank you so much, Cordin. We've got a few more questions there. We'll get those off to Cordin. We'll try and get some answers and add them to the presentation. And when we circulate that one, so sorry for the trouble there. Cordin, many thanks for that presentation. Once again, I think you've given us something of a Bible that we can rely on and utilize and guide what we're planning here. Gary, we need a lot more research here. I think this really shows that we're slipping. We're definitely slipping with this high temperature stuff in Australia. So we need to get some things going.
On that slide, we'll have an Australian company up there on one of those slides of the different companies and the technologies. So
absolutely, but at the very least, we do have GTET here in Australia, who's have now launched this low pressure steam heat pump. It's coming out of Europe. GTET does have a lot of their own designs and things, but they've got this module out of Europe, as I understand. And so, yeah, we've at least got this available. So, looking at about 800 kilowatt or so skid there, producing steam at 150 odd degrees. So there we go. At least we've got something available and supported locally. So that's something there. To finish off with, just to let you know, it is Heat Pump Month with A2EP. We've got a whole heap coming at you. Next week, we've got another webinar talking about modeling, optimizing, and integrating heat pumps, how do you get the most out of them. We'll look at solar PV thermal and how you could integrate that with your heat pump. There's a project at the North Sydney Olympic Swimming Centre that are going to use that, and let's take a look at that one from Cool Sheet. After that, on the 20th of March, we're just going to hit you with dozens of installations and more case studies of sites using heat pumps from locally and around the world. You'll get a heap of case studies on that one. On the 27th of March, we're up in Brisbane for a site tour. We're going to check out a heat pump at an aquatic centre, followed by some bioenergy visits for looking at a biogas and anaerobic digestion with Griffith Uni, and looking at a site creating biochar. And then at the end of the month, we're not finished yet, we're going to go look at geothermal. We haven't done much with ground source heat pumps. We're going to do a webinar dedicated to that one. One other thing for members, on the 14th of March, we're doing that to one of our arena collaboration pods, trying to help people access funding so that they can go after projects just like this. And so that's it from us today. If you want more of A2EP, hit us up on LinkedIn. But it's always left to say is thank you very much, Dr. Cordin and Professor Gary, for joining us today. A wonderful presentation and webinar. But to everyone else, thanks for joining, and hope you have a very nice afternoon. Thank you and goodbye.